Alright, let's talk about directional derivatives. Right? Let's find the derivative of function f of x comma y comma z in the direction of a unit vector u is equal to a comma b comma c. Right? So let's say you're moving from at the point x comma y comma z in the direction of u. Right? So if you want to write the x comma y comma z as x comma y comma z, as simply start from x0 comma y0 comma z0, then you add any multiple, constant multiple, so it's a t times u, a comma y comma c. Right? Then we want to take the derivative of f. Let's see, it's going to be a derivative of f with respect to, say, t. Right? Then we know that we would have to do a partial of f with respect to x multiplied by derivative of x with respect to t plus partial of f with respect to y times derivative of y with respect to t plus partial of f with respect to z times derivative of z with respect to t. Right? So you can see that we can rewrite this guy as, right, so this is just a dot product between partial of f with respect to x comma partial of f with respect to y comma partial of f with respect to z, which is the gradient. So this is just going to be a gradient of f, and take the dot product with partial of x with respect to t would be a, and partial of y with respect to t would be b, and partial of z with respect to t would be just c. Right? So this is just going to be the unit vector u. So the directional vector is just simply gradient of f dot product with direction vector u. Alright, so let's look at a simple example. Let's say f of x comma y comma z is equal to x squared y plus xz. Then we want to find the directional derivative in the direction v equals 2 comma negative 2 comma 1 at the point 1 comma 2 comma negative 1. Right? So first we need to find the gradient. So let's go ahead and find out. The gradient of f is equal to, right, partial of this guy with respect to x. So that will be 2xy plus z, right? Partial with respect to y would be x squared. Partial with respect to z would be x, right? And then we want to evaluate this guy at, maybe I'll go ahead and do that. Evaluate this guy at 1 comma 2 comma negative 1. Alright, so that will be what? Let's see, 2 times 1 times 2, so that's 4 minus 1, so that's 3. And then x squared, so 1 squared would be 1, and x, so another 1. Right? So that's the gradient there. Then we would have to, let's see, rescale it so that we have a unit vector. So unit vector u, direction vector u would be v divided by its own length. Right? So that would be, let's see, you have a 2 comma negative 2 comma 1 over, right, square root of 2 squared is 4, negative 2 squared would be another 4, 1 squared is 1, so that's square root of 9, which is 3. So this is just going to be a 1/3 2 comma negative 2 comma 1. Right? So therefore, So if you want to find a directional vector, maybe I'll use this notation. So this is going to be a derivative and direction of u of f. So that's going to be 3 comma 1 comma 1 dot product with 1/3 2 comma negative 2 comma 1. Alright, so that's going to be 1/3 is pulled out, 3 times 2 is 6, plus 1 times negative 2 is negative 2, and maybe I'll just write it as a minus 2. Let's see, this minus 2, and 1 times 1 is 1. Right? So it's going to be, it's 4 plus 1, 5, so it's going to be 5/3. Right? So 5/3 is the directional derivative of this given function f. Right? Alright, which means that as you move in the direction of v, and the function value increases by 5/3. Alright, that's it. I hope that this was clear.